A problem a lot of science teachers face is that they come into a lab and they find a bunch of things that they don't know where they came from or what they're for. Sometimes when science teachers create something for a lab, they don't always label it because they know what it means, and then a new science teacher takes over in the lab and they're kind of lost. So the science teacher that was here before me created several petri dishes with some ionic compounds to do a flame test, and most of them are labeled, except for this one. So I'm going to do an experiment to try to figure out what it is. I know the materials I have are for a flame test, and they were mixed with chlorine, so I went through the cabinets and I figured out what substances that are bonded with chlorine I have in my chemical cabinet that I don't have in these samples. So I narrowed down and I'm going to do a little flame test to figure out what my mystery substance is. What do you think the mystery substance was? Now you may be wondering why these ionic compounds are producing different colors of light in the first place. I went over it a little bit in my fireworks video, but here's the Reader's Digest version. So you have your nucleus of your atom, and you have different energy levels. Your electrons will fill up the energy levels until you run out of electrons, and then your outermost electrons, your valence electrons, will be sitting at the lowest possible energy level. That's called the ground state. The ground state's nice and stable. But sometimes you'll come along and you'll add energy. How much energy comes in will determine how high the electron jumps. More energy, bigger jump. Less energy, smaller jump. The electron will only jump to other energy levels. It will not sit here. It will be on this one, or for more energy this one, or a lot of energy this one. So the electron is sitting there. A lot of energy comes in from something like, I don't know, a Bunsen burner, perhaps. And so the electron jumps. Boop. This jump is called a quantum jump. Because of the quantum jump, the electron is now at a higher state. That's called the excited state. Woo-hoo! Unfortunately, as with a lot of excited states in our lives, that's unstable. Because it's unstable, the electron's going to fall back down. Well, energy came in to make the electron do the jump, and conservation of energy, energy in, energy out, the energy is going to be emitted in a particle of light. We call this a photon. It's like a little packet of energy. Light acts as both a wave and a particle, so we think of a photon as a little packet or particle of waves, a little wave packet. Different sized jumps will produce different wavelengths of light. The equation we use for energy is E equals h nu. H is Planck's constant, so it stays the same. And if you look at the equation, if nu goes up, the energy goes up. Nu represents your frequency, so as energy goes up, frequency also goes up. C is the speed of light, lambda is the wavelength, and nu, again, is the frequency. So since speed of light is constant, as frequency goes down, wavelength goes up, or as wavelength goes down, frequency goes up. So that tells me that if the energy goes up, the wavelength goes down, and vice versa. So as energy goes up, wavelength goes down. As energy goes down, wavelength goes up. Visible light is measured on a spectrum. The wavelength of purple and blue light is much smaller than the wavelength of red light. So the numbers here for red light are much bigger than the numbers here for yellow and green, and much bigger than numbers for blue and purple. A big energy jump is going to emit blue or purple light when it falls back down. A small energy jump is going to emit something closer to red when it falls back down. Lambda. So this is why now you